This time, ladies and gents, let's talk about how in the world can you convert energy into mass and mass into energy. We talked about the many wonderful accomplishments of Albert Einstein, and this is the most famous equation in the world. What does it mean? Well, E equals mc squared. In this equation, E stands for energy, m stands for mass, and little c stands for the speed of light. The speed of light is the fastest thing that we know about. It's a very big number, 3 times 10 to the 8th meters per second, or over 180,000 miles per second. But what this equation says is that matter and energy are interchangeable. Until Einstein, that was not an idea that anybody had even imagined. And he said you can convert one into the other. Now, in your everyday experiences and my everyday experiences, we don't see this happening. In order for energy to convert into matter, you have to have incredibly high temperatures, like the temperatures you get in a star, and incredibly high pressures. So this E equals mc squared was the key to determining how stars are powered. There are 2 different ways that you can have a nuclear reaction. And nuclear reactions involve not the electrons that are on the outside of an atom, but they involve the nucleus at that center that contains protons and neutrons. Typically in a chemical reaction, you're just involving those outside electrons. But a nuclear reaction, you're involving that chunky little hard center of the nucleus that contains neutrons and protons. There are 2 different types of nuclear energy conversions. One is called fission and the other one is called fusion. We're going to spend most of our time talking about fusion because this is what powers stars. But I want to take a moment and talk to you about nuclear fission because mankind has been doing this since well before the 1940s. Fission involves taking very large atoms, breaking them apart into smaller pieces, and this releases large quantities of energy. Fission reactions are what are used in nuclear power plants that are all over the country, and this is the process that happens to be used in atomic bombs. A typical fission reaction will involve something like a uranium atom that gets struck by a neutron, and that little neutron hits the uranium, breaks it into some smaller pieces, and releases energy in the forms of heat and light. Lots of heat and lots of light. The other version is fusion. Fusion, it sounds a little crazy, but it is the exact opposite of fission. Nuclear fusion means that you fuse or glue together small atoms to make larger atoms and release energy. This is what happens in the sun and stars. On planet Earth, this is what was used to create hydrogen bombs or H-bombs back in the 1950s. And quite honestly, this is a huge hope for answering all of the energy needs of mankind. If we can harness nuclear fusion, the fuel is hydrogen. And we have 2 hydrogen atoms in every molecule of water. And we have a lot of water on planet Earth. Why is this tricky? Because in order to do this, we have to have the heat and the pressures like those that exist in a star. Now, why do I have Marty McFly over here from Back in the Future? Because when he does come back from the future, he has a Mr. Fusion home reactor on his DeLorean. So next time you watch that movie, watch for it. So in order to explain fusion, let's go back and recall some of the other science we already know. Main sequence stars, like our sun, are made of mostly hydrogen, lots and lots of hydrogen, and a small quantity of helium, plus some other bits and pieces. Hydrogen atoms are incredibly simple. A hydrogen atom contains 1 electron and 1 proton, simplest form of matter that there is. Now, if you recall from your basic elementary school electricity, you know that like charges repel and unlike charges attract. Meaning, if you have a positive and a negative charge, those 2 things are going to be attracted together. If you have 2 like charges, 2 positives, or two negatives, they're going to repel each other, as illustrated by this picture of this young girl. I think she's sitting on a like a trampoline or something with a canvas or vinyl bottom, and just by scooching around, each one of her hairs has picked up a static electric charge, and they are all kind of puffed around her, and she looks like a big dandelion fluff. One of the questions that scientists have asked for 100 years is this. Okay, we know like charges repel. We know that. Like charges repel each other. So why don't large nuclei rip themselves apart? If you have a hydrogen nucleus, it's going to contain one electron and one proton. No big deal, pretty simple. But if you have a larger atom, it's going to contain many, many protons. For example, oxygen contains 6 protons. That is 6 positively charged particles that are in very close proximity to each other. If you remember from chemistry, one of my favorite analogies is that if an atom was the size of a football stadium, the nucleus is the size of a little fly flying around center field about the 50-yard line. Now that is very, very tiny. So what that means is these protons are very close together. Scientists for a long time said, this doesn't make sense. Like charges should repel, and yet nuclei hang together. So what's up? Early part of the 19th century, another force was discovered, one that scientists did not know previously, and they called it the strong force. The strong because of the fact that it is the strongest known force. The strong force has a very short range of distance. It only acts, as a matter of fact, within the nuclei of individual atoms. Now, if you have the nucleus of an atom, lots and lots of protons in there, lots of positive charges, electrically, that atom nucleus is trying to pull itself apart. But there is an additional strong force, and this strong force is holding the nucleus together. Now, how do we even know the strong force is there? The strong force actually manifests itself, or can be detected, because it produces a small quantity of additional mass within the nucleus. And what we're leading towards is this E equals mc squared. So if you have a nuclei that has got a little extra mass in it, that little extra mass is actually the strong force that holds the nucleus together. In nuclear fusion, here's the sort of thing that happens. We fuse or glue together small atoms like hydrogen. And if you take a couple hydrogen atoms, and we're talking for an example here of heavy hydrogen, a heavy hydrogen atom is actually going to contain 2 protons, 2 neutrons, and 2 electrons if we have 2 of them. And if we take 2 of those and we fuse them together, what you're going to end up with is a helium atom. Now the helium atom is going to contain 2 protons, 2 neutrons, and 2 electrons. Exactly the same pieces. Here's the weird part. In the act of gluing all of these pieces together and reconfiguring them from hydrogen into helium, what you end up with is a release of excess mass. This weighs less than the sum of the parts. That seems a little counterintuitive, seems a lot counterintuitive, but Einstein is the one who figured out how this works. To kind of give you an analogy, here's another way of looking at it. Let's say that I had a car, and I was taking all of the individual pieces of the cars, every nut, every bolt, every wheel, every door panel, and all of those pieces of car I weighed. If I then put the car together, it would weigh less than all of the parts. All of the parts would weigh more. What's going on? There is an extra little tiny bit of mass. This extra tiny little bit of mass gets converted into energy via E equals mc squared. And that extra bit of energy is what powers stars. So in nuclear fusion, and you definitely need to know the definition of this, in nuclear fusion, this is the process of making bigger atoms out of littler atoms. And in the process of doing that, there is some extra mass that gets converted into energy via the equation E equals mc squared. Now, when we say it releases energy, what kind of energy does it release? Well, it basically releases lots and lots of heat. Heat is the speed or the velocity of molecules, how fast they're actually moving, and lots of light. So the two primary products of our star are a lot of heat and a lot of light, which is wonderful because that's what we need from our sun in order to be powered here on planet Earth. You don't get nuclear fusion in everyday occurrences. You have to have very high temperatures in order for this to occur. So if you start with a nebula, you start with a big cloud of dust and gas, and due to gravity and some sort of a trigger, and that trigger could be some sort of a gravity wave or a spiral density wave, or something occurs that makes this cloud start to collapse. When you have those particles get really close together, they are going to get very hot. And when the internal temperature of that cloud gets to somewhere in the neighborhood of 20 million degrees Kelvin, which is nutty and incredibly hot, almost unimaginably hot, then the particles are so close together, the hydrogen atoms are so close together with their individual protons and electrons, that the push and the pressure is big enough to start fusing protons with extra protons. They can get close enough for that strong force to take over and actually start creating fusion and releasing energy. So we start with a cloud about the diameter of the sun. You end up with something about the diameter of our star, and we eventually get something that will release energy in the form of heat and light. That will do it for this video, and we're going to come back next time and we're going to talk a little bit about nuclear synthesis.